Welcome back everybody to another video lecture from Miss Semino. This evening we're going to be having the second video in the Stoichiometry series, and just a quick review: if you're in regular chem it's going to cover chapter 12, and if you're in honors chem this is in chapter 9. And this video we're going to definitely be going over how to convert those stoichiometry problems, or I should say how to solve those stoichiometry problems using several conversion factors. So go ahead and please take as much time as you need. Make sure you're pausing, make sure you're writing down and asking questions tomorrow if you're not understanding what's going on. So the formal objectives for today's video is to construct mole ratios, this is a big term, from balanced chemical equations and apply these ratios in mole-to-mole stoichiometric calculations, to calculate stoichiometric quantities from balanced chemical equations using units of moles, mass, representative particles, and volumes of gases. And I know that these seem like, okay, only 2 objectives, not too bad, but this is a lot of calculations are going on, so please pay attention to how we're setting up the problems. So first off, we have mole-to-mole conversions, and we have this chemical formula here where we have 2 moles of aluminum oxide yields 4 moles of aluminum and 3 moles of oxygen. So it basically just means here that each time we use 2 moles of aluminum oxide, we also make 3 moles of oxygen. So notice we've got, every time we use 2 moles of this, we produce 3 moles of oxygen. So here's our little chemical formula again. The same thing, 2 moles of aluminum oxide, 4 moles of aluminum, 3 moles of oxygen. So basically, again, 2 moles of aluminum oxide are used, and it produces 3 moles of oxygen. So we can use this thing called the molar ratio here. So again, we're looking at these coefficients here for these values. So basically, we can say that 2 moles of aluminum oxide is basically equivalent to 3 moles of oxygen because they're being produced. So remember what we can do with equalities is we can set them up in ratios. So we could set this one equality up as being 2 moles of aluminum oxide over 3 moles of oxygen. Or we can flip that conversion factor over and we can say 3 moles of oxygen for every 2 moles of aluminum oxide. So here in this example problem of mole-to-mole conversions, we have some acetylene. This is used in welding torch, and it is burning. So I should say 2 moles of acetylene are burning with 5 moles of oxygen, yields 4 moles of carbon dioxide and 2 moles of water. So hopefully, as a quick review, you're noticing, oh, that's a combustion reaction from the previous chapter. But more to the point, it says if 3.84 moles of acetylene are burned, how many moles of oxygen are needed? And well, here's the answer, but let's click to the next slide and see how we would calculate that. So here I've rewritten the equation, and then I've gone back to what the question was asking us. It says if we have 3.84 moles of acetylene, how many moles of oxygen do we need? And so this is obviously going to be a mole-to-mole conversion. So as always, you want to start off with your given, which is the 3.84 moles of acetylene. And then we set up our conversion factor, and I'm hoping that you're remembering whatever your unit for your given is, it's going to go on the bottom. So I'm going to put moles of acetylene here on the bottom. And then I'm trying to get into moles of oxygen, so that's going to go on the top. And then now here's the tricky part. Well, what are the values that we're putting in here? Well, what you need to do here is you need to look at what your coefficient is. So let's look at oxygen, and we have a 5 coefficient in the front. So I'm going to put a 5 here. And then let's look at our acetylene. It's a 2 in the front, so I'm going to put a 2 here. So the math on this, it's going to be 3.84 moles. Okay, 3.84 times 5 divided by 2 because it's on the bottom. Just go ahead and do the math. And I'm hoping that you came out with a value on your calculator that says 9.6. And so remember, this isn't quite the correct answer because we want to look at our given. How many sig figs do we have? We have 3 sig figs. So this really, the real answer here is going to be 9.60 moles of oxygen. And again, it always helps if you box the answer. So just a quick review of how I solved this problem. You're going to take your given, whatever your given units are, it's going to go on the bottom because these given units will then cancel out. leaving us in moles of oxygen, and that's what we wanted our answer in. And this thing here that I'm boxing right now is called the mole ratio, and that's what helped us convert from moles to moles. So let's go ahead and look at the second example problem here. It says how many moles of acetylene are needed to produce 8.95 moles of water. And so let's just go ahead and take a look on the next slide of how to solve this. So again, I've just simply rewritten the chemical equation, and for me I always kind of like to draw a picture to see what I'm supposed to be doing, but remember the problem said, hey, how many moles of acetylene are needed to produce 8.95 moles of water? So they're giving you this amount here, and they're asking you for how many moles of acetylene. So again, it's a mole to mole problem, and we want to go ahead and start off again by writing our given. So we've got 8.95 moles of water. We want to set up our conversion factor again by putting our moles of our given, or our unit of our given on the bottom, which happens to be moles of water. And I'm trying to get into moles of acetylene. So again, we're setting up our mole ratio here, and in order to set up the mole ratio, you need to look for what the coefficient is in front of the water. So up here, we've got a 2, so I'm going to put a 2 here. Now let's look for our coefficient in front of acetylene. It's also a 2. And so hopefully you don't even really need to do any calculations because these are going to cancel out. But if you wanted to do some math, you could go 8.95 times 2 divided by 2. And your final answer for this is going to be 8.95 moles. And notice that these were canceling out. We were just left in moles of acetylene. So our answer is 8.95 moles of acetylene. This is our final answer. And again, just a quick sig fig check. We have 3 sig figs here, 3 sig figs here, so we're good. So now we're going to go ahead and look at the third example, and I would like you guys to try this one on your own, and then the next slide we'll go ahead and explain how to solve it. So for this one, it says if you have 2.47 moles of acetylene are burned, how many moles of carbon dioxide are formed? And I realize the answer is here, but just try to solve it on your own. So you're going from moles of acetylene to moles of carbon dioxide. So remember, use those coefficients to make that mole ratio. So hopefully you've solved it on your own and you're just here to double check. So as always, we're just going to start off with our given, which is 2.47 moles of acetylene. Then I want to go ahead and set up that conversion factor, and remember my given units, and my given units in this case are moles of acetylene. We'll go on the bottom, and then I need to get into my moles of my answer, so moles of carbon dioxide. And then we're going to go ahead and look at the coefficients to make the mole ratio. And so the coefficient in front of carbon dioxide is 4, so that's the number that I plug in here. The coefficient in front of acetylene is 2, so that's the number that I plug in here. And we just go ahead and do the math on this. And hopefully you did come up with an answer after you did the math of 2.47 times 4 divided by 2 of 4.94 moles. So our answer is going to be 4.94 moles of carbon dioxide, and that's how we would write our answer. And of course we want to go ahead and box it. So this mole-to-mole ratio is at the heart of how to do these stoichiometric problems. What you want to make sure, it says, how do you get good at this? Well, it just requires lots of practice. So it's just going to require doing like all the practice problems, maybe if you're still struggling doing the example problems in the textbook. So while mole ratios is at the heart of these stoichiometric problems, we're going to be able to do some other calculations for them, but they all are going to follow these basic steps. The first thing is you want to make sure you have a correctly balanced chemical equation. You want to convert the given amount into moles. Moles is like our intermediary unit, as you'll see in a second. You want to set up the mole ratios. You want to use mole ratios to calculate moles of a desired chemical, and then convert the moles back into the final unit. So one of the things that you're going to be wanting to include on your periodic table to help you do these stoichiometry problems on the test is this stoichiometry flow chart. Sometimes I call it a roadmap because it just kind of shows you where you are and then how to get there. So the problems that we just did, we had a substance and it was in moles of A, and then they wanted us to find moles of B, and so we simply did that using the mole ratio. But now what we're going to find is that we're going to be converting from grams to moles, and then from those moles to grams. So let me just go ahead and add another road map here. So if a problem gave you your given in grams of A, then asked you to find moles of B, well, you can get there, but it is going to require a couple of conversion factors. So what you're going to do is you're going to start off with your given, grams of A. You're going to use this conversion factor, moles over grams. That way the grams are canceling out. And you're like, well, what's this gram value supposed to be? It's going to be the molar mass of A. And then once you're in moles of A, you're going to have to convert to moles of B. And again, you're just going to use the mole ratio for that. And then, once you have it into moles of B, you can further convert it into grams of B by simply multiplying it by the molar mass over 1 mole. So let's go ahead and see how that's going to work in the next example problem. So here in this example problem of mass-to-mass problem, we can go ahead and read it. It says 6.5 grams of aluminum reacts with an excess amount of oxygen. And think of this kind of like a story problem, like where they're giving you like more information than you need. You just need to know you've got enough oxygen, so I'm just crossing that out. It's not going to be involved in your calculations. It goes on to say how many grams of aluminum oxide are formed. So we're starting off with 6.5 grams, that's your given, and our final answer is going to need to be in grams of aluminum oxide. That's what our final answer is going to be. So we go ahead and solve this problem by taking our given, by using that moles and grams, and notice the 26.98 grams of aluminum, that's the value that you're getting from the periodic table, or we might call the molar mass of aluminum. Now you're in moles of aluminum, because these units here would have canceled out. Now, once you're in moles of aluminum, you need to get into moles of aluminum oxide, using this mole ratio here. So our moles of aluminum are canceling. Now we've gotten into moles of aluminum oxide, and you might be wondering, where did you get these values 2 and 4 from? So remember, this mole ratio comes from looking at the coefficients. So if I find aluminum oxide in my chemical equation here, there's a 2 out in front. And then if I look at my aluminum, there's a 4 out in front. So that's where I got these values from. And then now that I'm in moles of aluminum oxide, that's nice, but that's not what the answer wanted. It wanted it in grams of aluminum oxide. So then I just have to use the molar mass of aluminum oxide to determine how many grams. And so the calculations here is going to be 6.5 times 1 times 2 times 101.96. Then hit the divide button for 26.98. Hit the divide button again for 4, and then you can divide by 1. And our final answer here is 12.3 grams of aluminum oxide are formed. Again, a nice nifty thing here is notice that there's 3 sig figs, so our answer is good. So here's another good example problem. And it says if we have 10.1 grams of iron are added to a solution of copper 2 sulfate, how many grams of solid copper would be formed? So I'm hoping that you're noticing that we're starting off with 10.1 grams of iron, and then we're looking for how much solid copper would be produced, so grams of solid copper. So I'm going to go ahead and box this because this is what I want my final answer to be in. So notice we've got our iron on this side, we have our copper on this side, and the answer here is 17.2 grams of copper. But of course the setup is important, so take a minute, try to solve this problem on your own, and then check the next slide for the answer. So here I just have our chemical equation again, and it's starting off with 10.1 grams of iron and asking, well, how many grams of copper will be formed in this chemical reaction? So sometimes what I like to do is just write myself like a little map or like a little pathway that I need to follow. So I am in grams of iron. I'm going to need to get to moles of iron because remember moles is our intermediary unit. Then once I'm in moles of iron, I need to get 2 moles of copper. And then once I'm in moles of copper, I can get 2 grams of copper. So think of that little road map we were just looking at. So of course I want to start off with my given, which was the 10.1 grams of iron. Then I'm going to multiply it, and hopefully you have that road map written down. And it's where the grams were on the bottom, moles were on the top. And if you look at the periodic table for iron, I'm looking at mine right now, and it says 55.8, so I'm just going to say 56. So good. Now my grams of iron will cancel out, and I'm in moles of iron. So now I need to get into, if we look back up here, from moles of iron to moles of copper. So I'm going to need that mole ratio to do that. So moles of copper, of course, will go on the top because that's what I'm looking for. I want my moles of iron on the bottom so it cancels out. So I need to go ahead then and look up at my equation here, and what's the coefficient I see in front of copper, and it's a 3, so I'm going to put a 3 there. Then if I come back over here and look at the coefficient in front of iron, it's a 2. So I'm going to put the 2 here. Well, that's good. Now my moles of iron have canceled out, and I am in moles of copper. And that's nice that we're in moles of copper, but that's not what our final answer needed to be in. It needed to be in grams of copper. So now I'm going to have to use the molar mass of copper to calculate the final answer here. And then I look at the periodic table for copper. Let's see, and it says 63.5, so again we're just going to kind of round and say 64 grams of copper for every 1 mole of it that there is. We're going to go ahead and do some math, and hopefully you are coming up with an answer that's 17.2 grams of copper. You want to box that answer. And again, I like that it has 3 sig figs here, 1, 2, 3, and our answer, and our given here had 1, 2, 3, so we know that we have the correct number of sig figs for our answer. So remember from the previous video, another way that we could look at chemical equations is look at them in units of volume. And so this says here, how many liters of methane at STP are required to completely react with 17.5 liters of oxygen. And so here's the chemical formula. And so what they're asking us to do is to go from liters to liters. So let's go ahead and go back to that flow chart that we were just looking at. So here I just rewrote the mole roadmap to maybe hopefully you'll be able to read it a little clearer. We said if we needed to go from grams of A to grams of B, these are the steps we would take, and these would be the conversion factors along the way. And now you can do the same thing with liters. So if I'm given liters of A, I can get to moles of A, and then I'll need to get into moles of B, and then I can get into liters of B, and that's what that last problem was asking us to do. So the conversion factor that's going to help us get there is, remember that 1 mole is equal to 22.4 liters at STP, and that meant for standard temperature and pressure. So we can use our conversion factor here, and it will be 1 mole over 22.4 liters to get us from here to here. Then again, I'll be now in moles of A. I can convert to moles of B, or the other substance that I needed, and then I can get into liters of B by using that very same conversion factor, but just flipping it over and going 22.4 liters divided by 1 mole. So let's go ahead and see how that's going to work out. So here I've just rewritten the problem, or the chemical equation again, and again it was asking us if we have 17.5 liters of oxygen, how many liters of methane would be needed to produce this amount. So as always, we want to start off by writing our given. In this case, it's 17.5 liters of oxygen. I'm going to use that conversion factor that I mentioned on the last slide, which is 1 mole is equal to 22.4 liters. And of course, we need to add our element there. So good, now my liters of oxygen are canceling, and now I'm in moles of oxygen, but I don't want to be in moles of oxygen, I need to get into liters of methane. So I need to get into moles of methane first, and then I need to cancel out my moles of oxygen, so that's why that's going to go on the bottom. And now here it's always the tricky part, like, well, where are you getting these values from, Miss Simino? So if we look in front of methane, there's no value there, so we assume that there is a 1. But if we look in front of oxygen, you're going to need 2. And then I'm going to go ahead and have to continue on my conversion factor on the bottom here. So these moles of oxygen cancel out. I'm in moles of methane, which is good, but I need to be in liters of methane. So I'm still going to have one more conversion factor where I go 22.4 liters of methane divided by 1 mole of methane. And then so when we work this out, we're going to notice that our moles are canceling here. And you should come out with a value that says 8.75 liters of methane are needed to completely react with your 17.5 liters of oxygen. So here's just a quick reminder. Avogadro told us that equal volumes of gas at the same temperature and pressure contain the same number of particles. This is a biggie here. Okay, they have the same number of particles. Moles are numbers of particles, also a biggie, and you can treat reactions as if they happen in liters at a time as long as you keep the temperature and pressure the same. So that's why in these liter problems you'll always, well not always, but you'll mostly see them say at STP, meaning standard temperature and pressure. So while I know that this has been a long video, I hope that the examples better help you solve those stoichiometric problems that we're going to be working on. And good luck.